So our next speaker is going to be David Belanger. He's a senior research fellow at the Stevens Institute of Technology, and he's also former vice president of information, software, and systems research at AT&T Bell Labs, and he's from New Jersey, so he's going to talk to us here. Go ahead.
Thank you. I'm going to approach the subject from a little bit different point of view, largely from the data point of view, so much softer. I will depend on Mung, Tao, and Tom to take care of the architecture and the hardware for me. And the other thing that I'm going to approach this from is from the point of view of making sure that we can actually deploy these things and operate them. So having spent 20 odd years doing big data for a telco, we understand very clearly that these things just don't happen to work when you get them out there. You have to worry a lot about whether, for instance, the data is drifting. It no longer is what you use to build your learning models on. There are a whole bunch of issues that derive from the way big data is done. That in the very distributed fog architecture, in cloud architecture, or even in more classical architectures, get disrupted by the fact that learning machines are essentially the devices that we're using to build the software. And so, looking at this from a data point of view, we look at the cycle that's in the middle there. Monitor data, analyze it, decide, control, instrument. On the left, it says IoT. It could be the human crowd. It could be various fog sensor devices. On the right is big data, what we do with the data. And if you look at big data today, much of what goes on, you'll see, is the top of this. It's monitor, analyze, and decide. Control is going to fundamentally change how we think about how we put these systems together. Over time, in fact, at least for the last decade, there have been a lot of systems that have simply too much data to bring back centrally so that you had to do processing on the edge, or sampling. You could do processing on the edge, assuming that the data could be partitioned horizontally. So things like telephony fraud you could do on the edge for landline telephones. You couldn't do it as easily for credit card fraud because one can use the credit card anywhere. So the edge that you actually put your credit card into could be anywhere in the world. It doesn't partition as well horizontally. So what we're seeing, and what we will see far more of, is a partition of what we can do on the edge, what we have to do centrally, based on the semantics of the data that's involved. And in addition, at least in my experience, almost no big data activity takes place with one data set or one data stream. It involves the classical databases that corporations have. It involves open data. It involves all sorts of data that needs to be integrated together. In that case, what we're looking at is doing what we can semantically on the edge, because that provides us with the latency that you've already described, heard described. But much of the machine learning that we do will have to be brought back at least one or two levels in a hierarchy. And I'll show you a picture of that in a little while. This is just the way data scientists think of doing big data. And I think any of you who have been involved in data science know this. You start with data and you clean it up. You store it, compress it, do whatever you have to do analysis on it. Nowadays, with big data, that's probably dominantly machine learning techniques. And then you create a model which can be used for classification, regression, anything else. It turns out that when we want to move these systems into production, that's the first box in this process. And the second box is we have to get the architecture right. And certainly the previous three speakers are far more qualified than I to help get the architecture right. But it has to be right, and it has to have sufficient APIs that it can work with not only the things we're putting in place, but the things that are already in place, et cetera. Then it has to be tested. We all know about unit test, integration test. It has to be tested with the system because its various partners within its ecosystem are going to change over time. There has to be change management to take care of this, deployment, operations, and maintenance. Underlying point here is that these things are part of very large systems. The very large systems were not built in a green field for the most part, and so these are part of systems that have fairly long histories. So here's a very complicated picture, but it's a picture that in some sense tells a story of how these systems can be thought of and built, or at least some of them. So from the left, we have data coming in. It could be data that's coming in a very distributed way. In the edge, it could be data that's actually coming into a central location. But we have these little boxes, all of which are models, which are have been created to do something with that data, do it quickly, and take action on it, do control. So in security, might raise an alarm, might start to throttle various areas. In fraud, might cancel your credit card for you, or whatever else would make sense. But these are devices that are designed to do things very, very quickly with only as much persistent storage as they absolutely need, and only as much persistent storage as they're likely to get either directly from their own input or supplied from the core. Now, if you go, and we'll see how long this laser points. Well, so this red boundary is essentially thought of as, from the data's semantic point of view, the edge, and probably from the architecture's point of view, close to the edge in hierarchy. On the other hand, there's the blue boundary. I've labeled it cloud, but it could be anywhere further down in the hierarchy, in which case learning models are created. And basically, in many cases, these models are created to use things like graphs, relationships, which would not be available further up in the hierarchy. And their role is, often overnight, to pump out new models to the edge. In fraud systems, for instance, the systems would look at specific credit card numbers, specific phone numbers, and have a model for each of those. So they might pump out millions of these things to appropriate places and probably do it on a nightly basis. But the point is that that section is more aggregate. It requires very detailed information, and it is designed to provide very quickly executing models to the edge. In addition, in terms of operation, it has to be designed to know when it needs to update the models. And this is one of the big challenges in terms of doing big data in a fairly real-time and very distributed environment. And that is that data drifts. It changes its nature. It's not easy in fairly opaque modeling techniques like neural nets, like deep learning, et cetera, to determine when the data drift has actually caused a change in what you're doing. So techniques are being developed, and a lot of research is going on right now to determine how we detect when the models that are out at the edge need to be changed. And finally, well, I don't know if it reaches that far, but up on the top in orange are a whole collection of systems that are already there. In this picture is a medical picture. We have patients being monitored. We have patients being treated automatically, data issues from the fog and cloud, for instance, sharing data, standards for data, standards for the metadata. Most industries have created huge groups of standards so that they can share data amongst themselves. In this case, there's going to be a lot more sharing and a lot more granularity of sharing of the data. The ecosystem we're looking at, we're right now in a second generation of big data. The software is very, very distributed. So think of things like Cassandra and Mongo. The databases are very distributed, not distributed enough to run at the highest edge of fog, probably, but that distribution and the horizontal partitioning that fog represents for data have to be reconciled. I don't think I need to mention all of the areas that might be involved. Finally, down at the bottom, what's needed? We need to understand how these systems that we build fit within the ecosystem that they're built into. They're going to be fully automated. You hear terms like DevOps, and the companies who are involved in this, a lot of companies have to do it already without standards, are doing DevOps fairly routinely. We have to understand how the data itself partitioned, how the semantics of the data works. And finally, we need the skills to not only build the machine learning systems, build the systems which will actually do the control, but embed them as large software systems into even larger systems. Thank you.
Thank you, David.
Panasonic.